Well, hello everyone, and welcome to today's Education Committee webinar called Achieving Net Zero Buildings, Utilizing the Power of Building Performance for Sustainable Success. So my name's Eric Calderup. I am a member of IBPSA-USA's Education Committee, and I'll be introducing today's speaker. Just a couple announcements. Today's session is being recorded and will be available through IBPSA-USA's YouTube channel. If you have any issues hearing our presentation, then please try calling in by phone instead of using computer audio. And this is a Zoom webinar, so you'll be muted and off camera during the session, but please go ahead and post questions in the Q&A feature. If you did want to use chat for anything, then note that the default is all panelists and attendees. So change that if you want to message the full group. So we welcome your questions, thoughts, and ideas. And I'd like to dive in with introducing today's first speaker. So our first speaker will be Devanshi Dadia. She is with Atelier 10, where she is an associate of the New York office, and she's also co-leader of the firm's energy analysis practice. She's got expertise in both sustainable and architectural design, and she has a deep interest in building energy performance. And she successfully managed some of Atelier 10's most ambitious projects, varying from academic facilities, commercial towers, and cultural buildings. So I'd like to hand it off to you, Devanshi. Thank you for being here.
Thanks, Eric. Yeah, I'm excited to be here and looking forward to present to you about the Fellows Hall project in Williamstown, Massachusetts. So this is multi-unit housing student facility, which is roughly 15,000 square feet. It's located in Williamstown, as I mentioned, owned by the university, run by the university. It is pursuing the net zero energy certification this year. Just wanted to give you a time frame that the analysis was completed between 2015 and 2017. So all the stuff that you're seeing is predates all of the carbon discussions that we have been looking at lately. And the project was completed in 2019. So originally this building was supposed to be just a renovation project for the St. Anthony Hall. And the idea was that we did not want to have any increase in the overall energy use and build a new building at the same time. Eventually, we changed the proposal and we said that we would build a net zero dorm so that there is no net increase in energy use overall. When we set out to do our energy analysis, our discussions were mostly around what are our goals and what are our ambitions, how are we planning to achieve them. This project was meant for residents who are not necessarily from the state, and they're all coming from like warm and like climates from the equator. So they really were not really used to having these cold conditions. So thermal comfort was a priority. We wanted to make sure that our success was measured using data and energy simulation and measured data eventually. We knew that we wanted to have a net zero project, but not just for year one, but to also account for a buffer eventually, so that any variation in the operation and the climate would be accounted for in this analysis. We also had we had several opportunities, such as like we wanted to make sure that the massing was set right in from the beginning itself. And we also had challenges because this is a net zero project. So we had a limited roof area to begin with. So that was one of the bigger challenges that we knew we had to deal with. And then, of course, with the dorm facility, you also have to think about the laundry and all of the appliances that go into a dorm facility, and that quickly adds up to the overall electricity consumption. And then service hot water is another big issue, which was something that we had to make sure that we had a strong understanding about. For tracking and benchmarking, we made sure that we were modeling during all design phases and verifying the bids and submittals so that we are on top of any kind of changes that are happening on the project, and so as to avoid last minute surprises. Overall, we had a lot of coordination between the design team members, and communication was really, really critical for a net zero project. We had a continuous feedback loop so that we can continuously provide guidance. Using our energy model as a reference, we were able to provide how would a certain decision impact the overall goal for net zero energy. In terms of the modeling tools and workflow, we tested, we used IES VE in the beginning. This was 2015 for early SD phase modeling, where we really evaluated all of the passive strategies using the IES software. And then as we transitioned and as we firmed up the design, we moved on to eQuest so that we could model the waterside systems a little bit more closely. Again, this was to make sure that we are overcoming certain limitations in the modeling tools back in the day. For PV generation potential studies, we used Rhino and Grasshopper so that we could account for shading and overshadowing, and we so that we could also account for the trees and the neighboring and the context more accurately. Overall, we first started with developing an energy budget with the available roof area and calculated the PV generation potential as a starting point. And we compared this with the energy use profile um, of a baseline, ASHRAE baseline energy model. So the black line is the line that shows the baseline consumption data, and the green, the shaded green portion here shows the on-site generation potential from the available roof area. And we very quickly knew that we had to look at several energy efficiency measures in order to make sure that we can hit our net zero energy goal. We started with a passive first approach, and we looked at, we performed an envelope sensitivity study where we tested several energy efficiency, several R values for the windows, walls, and roof in order to come up with an optimized performance for the envelope. And we looked at how much of an impact does that make to the annual HVAC savings so that we can we are not over insulating, but we are making sure that we are hitting that sweet spot beyond which the envelope does not make a difference. Along with that, we continuously coordinated with the architects to review their architectural details to make sure that there are no thermal bridges, and if there are, we provided recommendations on how to avoid or tackle these thermal bridges or minimize the thermal breaks in the design. Next up, we also looked at how can we limit summertime cooling. With this climate, we knew that it was to our advantage, and the temperatures were not significantly high, but even so, we thought that we should look at the peak design day condition to evaluate how can we minimize summertime cooling by deploying natural ventilation and operable windows and looking at external shading. And in addition to that, we also looked at how can we further reduce the discomfort hours by implementing supplemental ventilation cooling strategies in the project. So overall, we did see there was a significant reduction in the discomfort hours as indicated by the graphs on the right. And all of these passive strategies helped us to make sure that our electricity consumption from mechanical cooling in dorm rooms was minimal. Along with those passive strategies, we then looked at several other energy efficiency measures to evaluate um, a pathway to achieve the net zero energy goal that we established. So here you're looking at the bar graphs where I think the base design had steam because this project had steam. But like when we are looking at an ASHRAE compliant baseline, the energy consumption was significantly higher, as discussed earlier, compared to what the roof can generate. And then as and how we implemented energy efficiency measures such as passive house envelope, natural ventilation, reductions in lighting and equipment, and looking at more efficient systems, which are all electric, we were able to gradually reduce the overall energy consumption. And then solar water heating system is also another um, um, measure that helped in reducing the domestic hot water requirement or the energy consumption by the domestic hot water in this project. Another thing that we looked at was the first cost for several variations of all the energy efficiency measures that we evaluated. Because space was a constraint, and we also wanted to make sure that we are not exceeding the PV requirement for this project. We were looking at the implications of an increase in first cost and compared that to an increase in first cost for PV. So for some scenarios, we found that often the lower first cost solution resulted in an increase in the first cost of additional PV required for the project. While in some cases, such as these HVAC alternatives, we found that there are lower first cost solutions which are energy efficient and does not result in an increase in PV requirement. So this kind of helped the design team to take decisions around first cost as well, and to make sure that we are not compromising the net zero energy goal at the same time. For the PV generation potential, as I mentioned, we use Grasshopper and Rhino to evaluate the context implications on the renewable electricity generation potential. And we found that when you add these trees, you're reducing the overall generation potential by around 7%, which is significant for a net zero project again. So making sure that we are understanding what our energy budget is again very critical when it comes to PV generation potential. One other thing that we looked at was the year-on-year degradation of the PV panels by themselves. We knew that it did not have to be net zero just in year one, but we wanted to make sure that it's net zero for all of the future years. So we wanted to account for a buffer in the energy production capacity. So the products that we were looking at, we were also comparing the percentage of degradation per year while making decisions on what products to use for a project. Overall, we were because this is a net zero project, we were constantly tracking assumptions. The operational schedules were reviewed several times during the energy modeling process, which plays a big role because considering this is a dorm building, there are times of the year when the students are not within the facility. So we wanted to make sure that we are also accounting for that to some extent, but then that decision kept changing consistently, and we had to make sure that we have buffer for students to be in the dorm during the summer months as well. The other big item was tracking the assumptions for the appliances. So we had a laundry list of all of the appliances that would go into this facility based on the occupancy that we knew about. And this was verified and reviewed by the university. Um, and even when we were looking at submittals, we were keeping an eye out for any large pieces of electricity hog equipment, so that we're not really missing our target at this point. The other big piece was the domestic hot water demand. Again, understanding the shower duration and the sink usage was very critical when identifying the overall daily total of hot water gallons that were used in this project, so that we can come up with an estimate for the hot water consumption and energy use. Overall, at 100% CD phase, we landed up with the design that was truly high performance with the modest window to wall ratio of 22%, R40 walls, R60 roof, making sure that our air leakage rate did not exceed the 0.6 ACH at 50 Pascal. We were following the passive house requirements. And we also made sure that there was blower door testing included in the commissioning requirements, which did come up lower than the 0.6 ACH when we evaluated it. The mechanical system for this project included geothermal well fields and ground source heat pumps. And the air side included dedicated outdoor air units with 4 pipe balance units for supplemental heating and cooling. For the domestic hot water, we tried hard to incorporate heat pump systems for heating, but then with the size constraints and the fact that we were not able to make the fact that we were not able to put in a centralized system made us switch to an electric hot water point of use system. And then a 129 kilowatt PV array was finally put in on this project in order to achieve the net zero goal. We came up with several recommended operational practices for the facilities as well as the students, so that the project continues to stay net zero, because usage is very, very critical in making sure, mindful usage is very critical in making sure that the project keeps hitting these goals year on year. And lastly, wanted to share the post-occupancy monitoring and verification. This was completed by another organization, which was hired by the university. So on the left, you're seeing the modeled predicted generation and predicted consumption data. And on the right, you're seeing the third-party verified commissioned actual consumption data on a monthly basis for the last year, which, although there is a difference between what was predicted and what was modeled, but it is fairly close to the analysis that we did. Yeah, thank you.
Thank you very much, Devanshi. We'll get to the SimBuild announcement towards the end. Dylan, you want to go ahead and share your slides while I introduce you? So Dylan Lamar, he's the owner and architect developer at Cultivate Incorporated, where he brings to life sustainable and affordable housing in Eugene, Springfield area in Oregon. He's also among the leading passive house design consultants in the country and has supported the design of numerous passive house, multifamily, and commercial developments nationally since 2007. So thank you very much for being here, Dylan.
Yeah, thanks for having me. So I'm getting over a cold, so I apologize if I sound a little nasally. but yeah, this is presenting kind of a side analysis we did on the Solera apartments. The Solera apartments are located near Albany, New York, and are an array of about a dozen 24-unit buildings, kind of walk-up apartments around around parking areas with early net zero goal. The first phase, I forget, was built in 2018, I believe, and it was built out in phases over the years. So we're not meeting Passive House standard here, but we're using the Passive House energy modeling tool to analyze the project. And the project has achieved net zero and is performing quite well. So I have a long background with Passive House and have been using the PHPP, which is the Passive House planning package, the original kind of Passive House energy modeling software from Germany. Been using that for a long time, so that's what I've kind of default to. And there was an interest as PIAS has switched over to WFEP and modeling the project according to both models and seeing, you know, is there a sizable difference between how these two models model this project, and so that was kind of the original reason for this study. And so I'll talk a little bit about the project. I know it's been, I believe it's been presented at this conference before. I know it's been presented at NYSERDA in New York State a lot. So I'll give a quick overview of the project, though, just to orient us. Basically, it's a 3-story double-loaded corridor walk-up apartments. There's 24 units per building. Mostly 2- and 1-bedroom properties, units, and of course the leaf blower comes now, so I apologize if there's background noise. The elevations has the south, the kind of long axis of the building is more or less oriented to the south within 15 degrees, and there's equal window to wall ratio on the south and north facades, but no fenestration on the east or west. It's a 2x6 construction with a mix of closed cell foam and bad insulation in the cavity, along with a zip sheathing, so a 1-inch of polyiso on the exterior continuous. We achieved a thermal break at the slab with the inset kind of sliver of foam you can see here, and I'll zoom in on that just a little bit. And then continuous foam underneath the entire slab as well. Up at the parapet, we have 7 inches of foam over the deck at minimum, and then some spray foam to kind of span the gap along the rim of those flat roof trusses. To quickly walk through kind of the design of the project, again, this is Albany area, so climate zone 5. In both models, we're following the standard assumptions of the modeling protocol. So with the PHPP, we're following a PHI protocol. With WFE, we're following PHIAS protocol. So we're using the heat. Those have the same heating and cooling set points. Very similar occupancy, a difference between 57 and 62 occupants. I mentioned the envelope. The windows are very affordable, double pane PVC single hung windows. I've been impressed. This particular window has been able to achieve air tightness below 1 ACH 50. I believe some of the buildings even hit 0.6. Even with these single hung type windows, I would never recommend this. I think this is an unusually high quality unit. Typically we want to recommend casement type or some kind of a positive compression seal at windows when we're trying to get to those levels of air tightness. It does have the low-E IO89 coating, so it performs as equivalent to a poorly performing triple pane window, if you will. For heating and cooling systems, we have 1-to-1 mini split heat pumps in each apartment. And then for also an ERV system that's central with kind of semi-centralized within the core of each stairwell that services a number of units. There's some direct exhaust at just a couple of bath fans in the project that weren't able to be connected to the ERV. For the water heating, we have a pretty elaborate solar water heating system on the roof and a very large tank. I want to say a 1,200 gallon tank, yeah. And then backup heating is a air water heat pump, a unitary type. Appliances are all Energy Star. One thing I will note on it for plug loads, FIAS has pretty clearly specified protocol for plug load assumptions. With the PHPP, there's not a standardized assumption. They basically trust the energy modeler to use data that's appropriate for that locale and that building usage. So you know, basically I made my estimate based on my experience, but that's a pretty wide variable that, depending on what you assume there, can really dramatically change the results. So I'll make that caveat. Lighting is a pretty standard efficiency, high efficiency lighting system, and then there is quite a bit of PV on the roof. So the side-by-side comparison into the two models, these are the primary passive house metrics here. In blue, we can see the PHPP model, and in green, the WFI model. Overall, the heating loads, heating demand and heating load were within a 14–15% discrepancy of one another. So that's pretty good. And the cooling side was a little bit less so, between 26 to 30% discrepancy between the two models. Again, I think a big part of that probably has to do with the plug load, the variability of that plug load assumption, and what's you know, it leaves a wide margin for potential differences in how the two will come out. Overall, though, the site EUI it matches pretty well between the two projects. That we came in within 1% of one another. So when we kind of zoom in at the very specifics of meeting the passive house standard, not that that was a project goal here, but if that were the goal, it does make a difference which standard you follow. I will also, just an asterisk here, these metrics have been normalized for the same reference floor area. So PHPP and WFI use different reference floor areas, but for this analysis in this graph here, we're using the same floor area. So that is kind of an apples to apples comparison. Looking more specifically at the passive house metrics in terms of which standard is more difficult to achieve. This is a question I often get from clients. It's really pretty close. So when we model based on the standards of the certification protocols with the two different tools, you can see, again, the heating demand load, cooling demand load, and then the primary and source energy metrics. They really align pretty well. The bar here shows the metric that's required, and our larger bar here is the consumption of this particular building. So if we were to try to achieve a passive house with this building, we'd have a hard time doing it under either protocol. And then finally, just again, kind of backing out and looking at the overall EUI, you know, a typical existing building, this is demand on the bottom and supply on the top. Typical existing building is going to have a pretty outlandish EUI in this climate zone. Code minimum would be around 29. Architecture 2030, at the time this was done in 2021, would have us meet around 20, and we're coming in right around 15 with both models. And then positive to the 19 in the production side. So big picture, whether you're going with a PHPP or WFI, whether it's PHI or FIAS, your protocols you're following, you're going to be meeting an overall pretty similar level of stringent energy efficiency. And I'll just leave it at that and leave some time for questions at the end.
Thank you very much, Dylan. Zhongdi, why don't you go ahead and start sharing your screen? So our third speaker is Zhongdi Chen. He is a building performance engineer with White and Company, and he performs energy modeling for net zero energy designs, energy code compliance, and third-party certifications. He also conducts related research in daylight modeling, and he's helped design 5 net zero energy projects and has played an integral role in leading Illinois' first and third net zero energy projects through the verification process. And perhaps we can ask him about what about the second one. But please give me a warm welcome, or please give a warm welcome to Zhongdi. Please take it away.
I can just answer the first question. So the second, it's just simply because some other company got it, so we got first and third.
Yeah, I figured that. But
Yeah.
Congratulations on the first and the third.
Yeah. So the project I bring today is the third one. So it is in Chicago area. So it's in Northbrook, Illinois, actually in the northeast corner of Illinois. Climate zone 5A condition. Design condition is -10 degrees in winter and 92-74 in summer. Ton of heating load, not much cooling load from external. So a little bit background for the building. So it's called TPAC. It is a Techni Prairie Activity Center. It's a gym. So the building is tall volume space, 32 feet high, basketball court and fitness center. We also have some fitness classroom on the second floor and a small admin area, which is the front little area here. So the building is 44,000 square foot with 20% window ratio. And most of the window are actually the curtain wall on the southeast corner and northeast corner. So we are looking north now. This is southeast corner. And because this is a commercial gym, so it operates 16 hours a day, which is a huge disadvantage for net zero projects. So this is a basketball court, and this is actually gym looking north. So big curtain wall. So this building emphasized on energy efficiency from very early stage because we had the idea of pursuing a net zero foundation grant. It's called Illinois Clean Energy Community Foundation. So this, in order to receive the grant, we must be net zero. We received $1.8 million for grant in total. This funded the premium cost of materials, design, and PV arrays to make it net zero. In order to apply for this grant, this building must be passive house certified. So we have R60 roof, R40 walls, and 0.12 COG glazing. It is not triple glazed, but it's almost semi-triple glazed. Only the center panel is not glass, it's plastic. And the tested average building air leak is 0.049 CFM per square foot at 50 Pascal. It is right below the passive house threshold. As for building system, we have air-to-air heat pump for majority of the building for all the tall volume space, and VRF-OS combination for the admin space. And we also have some unit heaters scattered around in stairs and vestibule, etc. So the model result is we are looking at 27 EUI without PV and negative 0.4 with PV. And the actual EUI we measured was 29 EUI without PV and negative 0.24 with PV. So this building managed to certify as net zero in the first 12 months of operation, which means this data we see here, including some bad data from the first couple of months. So after building is operated, there are problems. We find the problem, we fix them, but inevitably they will put a dent into the performance. So we did a lot of tweaks and adjustment to improve its performance. So the actual EUI for the building today should be actually even better than this number. This is when the building is certified and when we walked away from the project. So that's all for building overview. Now I have some energy model highlights and lesson learned during the design and post-occupancy period. Because we want to pursue net zero from day one, so energy model has been a very important piece in the early stage. And this is Chicago. winter is long and cold. PV production is terrible. We have too many clouds all year round. So we have learned from the past project that most likely we will have to cover the whole roof with PV. And this means our PV budget is pretty much fixed when the building massing is confirmed. So in this picture, we can see our whole roof is covered by PV. And we even put the PV on the lower roof, which is right next to the mechanical screen here. It gave a significant shade to this PV on the lower roof. It also shows how desperate we are. So we don't want to do any ground-mounted PV because it is just way too expensive compared to roof-mounted, and it will break our budget too fast. So this type of project is the energy model is so popular among the team. For example, I have the ultimate say on how much window this project can have. The 20% win-over ratio in this project was not simply because the architect wanted it. It is a careful compromise by multiple departments. So we want more outside view. We want good daylight, but we also need to be careful not to blow our energy budget. At the same time, passive house also have the threshold on heating load and cooling load. For our case, heating load is the one matters. And passive house is originally designed for residential buildings. So when we apply it to the commercial building, we do meet a lot of problems and very difficult to overcome. Unlike other projects, so this time we have a very clear energy consumption goal, which is how much PV energy we can produce. So trade-off between the components, it's become quite clear. So for example, more glazing means it must be better glazing. And if we place the window in a smart location, then it will lead to a daylight harvest, which can directly improve our energy consumption. So design process of different parts of the building are dynamic to each other. This is the way it should be in design, but unfortunately, in most of the projects, it doesn't happen. Everybody just working their own little bucket. Architect and mechanical engineer will sometimes ask for energy model input for several options they have selected. But as far as the total energy consumption, it is just usually what it is. And mechanical system is usually the most difficult part in energy model, especially for net zero project, because unlike permit or lead model, which is comparing different system, this time we're comparing to reality. For permit and lead model, a lot of details can be simplified as long as they are identical in both proposed and baseline. But in net zero project, this does not work. The best example in this project is the control on air-to-air heat pump. So in the equipment selection or manufacturer brochure, they claim their heat pump can run, their air-to-air heat pump can run and pump heat out of air when the temperature is as low as -10 degrees or even -20. So this is true and not true. But in energy model, we have to make an assumption for these air-to-air heat pump. When does the backup heat kicks on? And also we need to include the defrost cycle calculation. But how should we determine the correct assumption for these? It is not simple. So we had another net zero project before this one. It is very similar equipment serving similar space. We track the data constantly and adjust the settings to improve the performance. And what we found is if we use the factory setting of this air-to-air heat pump, gas-fired backup will kick on in the low 40s. And when the temperature gets into 30s, the gas will dominate the heat. So in the first project for the previous first winter for the previous project, the gas ran through the whole winter. The gas consumption was a couple times higher than the electric HVAC. In other words, the air-to-air heat pump didn't get much chance to run at all. And of course, our energy consumption was way higher than we expected. So after that, we changed the setting, including when to switch to backup heat and when to run defrost cycle, how long each defrost cycle should be, and how much outside air should the system take in while the system is on defrost cycle. So after we've done all of that, the next winter, our air-to-air heat pump can run all the way down to 0 degree with almost no gas heat needed. But of course, when the temperature going below 0, the gas is back on because it's just way too cold. This threshold 0 degree is not a random number. This is more like a compromising point after we communicate with the factory engineer of the equipment. So it is to optimize the performance, but not to put too much burden on the equipment. So this change is a huge boost to energy performance because although Chicago lower temperature is quite low, way below 0, but it only lasts a couple hundred hours in a year, actually below 0 degree. So this change reduced our gas consumption by more than 10 times. So with these lessons learned from previous project in this TPAC, we can confidently use this control logic in energy model because we know two projects are similar space, similar equipment, and we know how to set the equipment up, and we know it will work. So this is an example when modeling a net zero project. So not only the equipment parameter matters, the customization of your control will also make a huge impact. So if there is no previous project can refer to, so the best way I can think of is communicate with your commissioning agent as early as possible and as often as possible. So due to most of the net zero projects request verification these days, energy model efforts does not end with design. It is quite common for a net zero project enter service and find out I am way above my expectation. I'm consuming way too much energy. So there are many reasons for this. Some can be fixed, some are more difficult to fix, or sometimes it's simply because some of the equipment is broken. And surprise happens all the time. At that time, the team will have to come up with different ideas to fix this problem. Can you still hear me?
Yes,
Hello?
we got you. Yeah. Mm-hmm.
Okay, I lost connection on my desktop. So this is the last page, so it's okay. For example, in this project, I have several questions like this. For example, this is a gym, so people are here to do activities. I think they can survive on 64 degrees. How much energy can we save from that? This is the building owner asking me. And or this corridor looks too bright. Let's lower the dimming set point until somebody complains about it. So how much energy can we save from there, and what set point should we start from? Or VRF running whole night instead of running on setback to avoid morning warm-up? Which one is better from energy standpoint, and how much, or how much worse? So every single one of these may not be a huge impact to the final result, but after the building is already built, it is really hard to find something that can make huge improvement anyway. So we have to rely on all these small changes, point them all to the correct direction and move the needle. So for net zero project, energy model is not only a design tool, but also used to provide guidance on post-occupancy tweaks and adjustment. So these energy model results on small changes help the team to have a better understanding on how to run the building better in future projects, and also help them to think about how the building actually operates while they design the future projects. That's all I have. Thank you.
Thank you very much, Zhongdi. That was very interesting lessons learned. Interesting project and good insights. So yeah, I'd also ask people again, if you have some questions and comments, to please type them into the Q&A section. You could also, if you have something you want to say, raise your hand and we can unmute you and you can ask your question directly. We do have a question from Tomasz. I think, Zhongdi, this is specifically about your project. So the given window to wall ratio is the overall ratio for all walls, which I assume is correct, or each wall separately. And was window area optimized somehow by orientation. I also ask, Devanshi and Dylan, you can also come back online to deal with these questions.
Is that for me?
Yeah.
Okay. So this is 20 is the total number. So actually we have basketball court and the fitness center. So after our conversation, so we believe fitness center want more glazing. So all these big screen curtain walls you see in the picture was on the fitness center. The basketball court only have couple punch opening on the higher level. Actually, they are more for daylight than view. Because we assume all people are playing basketball, probably they won't want to see the outside view as much as the people doing fitness in the other room.
Thanks. So, I've got a question for any one of you or all of you, and that's, as an energy modeler, you've probably been involved in projects that were not net zero projects as well. And what are your thoughts on the difference in level of effort from your side in terms of analysis time, gathering input time, communicating with the owners? Do you have thoughts on the difference in level of effort compared to kind of you might call it traditional energy modeling project? Somebody want to take that one?
Yeah, I can go first. So roughly, I would think 7 to 8 times. And that is why how much effort you actually want to, because in the normal model, permit and lease, so all the assumptions are, as long as they are reasonable, they are fine. And if you're not sure too much about, especially on the occupancy part, what people will do there, as long as, for example, it's a school, as long as typical school activity, I can say that's fine. But if we're compared to reality, it's not fine. There may be summer hour, the summer hour maybe 10 hours, maybe they want to run 24-hour activities. Who knows? We need to know, we need to learn it. And the other part is sometimes in the design phase, even the client don't know how are they gonna operate the building. So that makes even more difficult. So we have to, judging on their past, we have to get an educated guess. That may not be accurate. That's why I say many times after the building is built, something happens, we have to find some way to compensate for this unexpected loss.
Thanks. Devanshi, do you have thoughts on that level of effort?
Yeah, no, I agree with Zhongdi. I've not been involved in the post-occupancy verification or like fixing what was wrong, but throughout the modeling process, it's more of an absolute analysis compared to the relative analysis that we are used to. So it's not like you're comparing it to a baseline, and it's not just a percentage reduction or a percentage savings discussion, but it's more about making sure that you're accounting for all of the smaller tidbits that go into the building, because anything that consumes energy needs to be accounted for in the net zero project. So yeah, it definitely requires a lot more effort compared to our regular energy models.
Dylan, I saw you nodding your head. I suppose, one of the issues here is we've got to help the team size the PV system to meet targets, and perhaps that adds extra work.
Yeah, I would also add to that. I agree with what they've said, but I would also add that net zero and what's required can really vary widely based on the building type and size. So most of my work is residential. And so if we're talking of, a sprawling single family house versus a, 6-story multifamily, that can really, achieving net zero for each of those two building types really means a very different thing in terms of how the effort required.
Yes, got that. Yeah, so Sumrit had a question about, this kind of gets to the topic of that Zhongdi was talking about with like actual equipment performance. How do you ensure that manufacturers' data you use in your energy models can account for the specs being given under optimal test conditions, and I'm guessing we probably don't have a perfect or easy answer to that, but any thoughts on how we kind of account for or ensure that our models are,
This
giving
is
realistic
really
performance?
Yeah, this is really difficult. So in this project, so I mentioned we do have a previous project with very similar system, very similar space. That's why we took advantage of. But that is true. The selection, they are not lying, but they are not telling the whole story. So that's the best way I would think is first you probably have to rely on your experience. So we learn a lot because we monitor the building after it's built. After monitoring several buildings, we cannot get a pattern. So we know this will not work, that will work. And no doubt if we run into a new type of system, I bet I will still like running blind. I don't know what's going on. And another thing I can think of is work with your commissioning agent more, because they are the guy in the field more. They probably see more equipment actually running. They may have a better idea. And also another thing is you have grab your factory engineer for the equipment, and they can actually make the changes. So in this project, we actually rely on our commission agent and the factory engineer to change the control sequence. So that which helped a lot. Commission agent can do that, but factory engineer can make sure you don't actually break it, because if you do too aggressive, equipment might have problems.
Right, thanks. Yeah, it strikes me that as we pursue electrification and are getting into using some, electric heating systems that we haven't used in the past, we are kind of into this frontier of uncertain or unknown performance. Devanshi, you had some thoughts on that?
Yeah, on the modeling side specifically, I can add that what we do request from the manufacturers are performance curves, and we look at what efficiency would the equipment operate at during different part load conditions, during different ambient conditions, or different condenser water temperatures, and then use the loads that the energy models produce to evaluate where would the efficiency land, even because the model curves and model inputs are not as flexible as we would like them to be, at least with the current energy modeling software that we're used to. So a lot of spreadsheet analysis also helps us to get an understanding of the overall operation of the system, especially if you're talking about the plant side.
Yeah, hopefully we'll, the availability of reliable performance data will improve. We've got a pretty good handle on chillers and boilers. We've been modeling those for a long time, but the various air-to-air heat pump and variable refrigerant flow systems are a little bit more of a frontier here. When you think about sort of another question here, you think about the role of the energy modeler and how it changes with these projects. I heard in a couple of these cases that, the energy modeler here is actually playing a role in some of the design decisions with regards to things like window area and insulation. And I guess one question is, do you find that having a net zero target kind of changes or increases the role of the energy modeler? And then another part of this question would be, if we all, as energy modelers, are to play this role better, what kind of education needs, what sort of things do we need to learn in order to help the industry, meet these goals? Maybe that's too big a question, but
yeah, my thoughts on this is also something I hope I did before was, as energy modeler, I should not be only sitting in the desk. I should go into the field, look at this equipment more and see how it works, other than just reading whatever the manufacturer says, because it is really different. When you talk to the actual people running the facility manager, they will tell you this actually doesn't work very often. And actually, I think for net zero, we talk about this in net zero, we are actually, it's quite confusing this word. We're actually doing two things at the same time. The first is making the building efficient on consumption side. The second is to install enough PV to cover that. So these two things are actually irrelevant. The net zero, this idea actually bound these two together, but actually these two are not dynamic at all. So I think as energy modeler, we are more focused on the first part, the consumption side, because the generation is seriously, it is depend on weather, and as long as your equipment doesn't break down, it is quite a passive system. There's nothing you can do with it unless it breaks down.
Right. Thanks for that. We've just got a couple more minutes here. That we did get a question from Rainiel. This is kind of specifically about technologies, renewable energy technology. So is building integrated photovoltaics still practical and effective, even though its efficiency is not promising? You know, I think here we're talking about, you know, other than the rooftop photovoltaics, but perhaps integrated into the facade or other features. Do you guys have thoughts or experience on, you know, whether that's going to work for projects?
I think in large projects, located in urban areas, this is still a viable technology. I agree that the efficiency is pretty low, but when you have minimal roof area and most of it is hogged by your mechanical penthouses, your cooling towers, etc., it's definitely an option to evaluate, especially if you have a facade that's oriented in the right direction. The amount of PV that could be generated, the amount of electricity that could be generated, even with the low efficiency building integrated PV, does contribute to some extent. So it's not something that I would dismiss just because its efficiency is low.
So we're just close to the end here. Before we hand it over to Lori, did you folks have any other thoughts, Dylan or Zhongdi or others, on this topic in general?
I would just add to that last question. You know, I think a lot of times we just take for granted that we're not going to be able to afford effective exterior shading on east and west facing windows, for example, and that's really a challenge, an assumption I really like to challenge, because when you do have a situation where you don't have a lot of roof area, but you do have a large facade and a lot of glazing, you know, that's a really great architectural challenge to come up with good operable shadings. We do it on, I've been developing affordable housing here where we do simple barn door shutters with unfinished cedar fence boards, and it's very cheap and it's very effective. And our post occupancy surveys find that the clients, the tenants, the actually owner residents really like it. To have that ability, both to control sun and also when they're against a busy street, they say it really decreases traffic noise. So, you know, moving back to these passive systems that don't, that engage the occupant and learning about their climate and their setting, and giving them some ability to control their environment is really nice. And of course, when you can take advantage of east-west facing passive solar gains in the winter, but preclude them in the summer, that's really a beautiful spot for an energy modeler to do. And we often just completely assume we can't do that. But if we can, you know, if you look at study an energy model, it really is a really valuable way to gain some BTUs in the when you want them and not when you don't. So anyway.
Thank you. Well, thank you to all three of you. I guess, Devanshi, would you mind pulling up that SimBuild slide to share again? And then I'll hand it over to Lori to close us out. Sorry to just spring that on you, Devanshi.
Okay, thank you. And on your screen, you'll see our promotion of our SimBuild conference that is coming in December. In Denver, May 21st to the 23rd of 2024. We are super excited about this event, and just as a reminder, the full papers deadline has been expanded to November 13th. Submissions are open to anyone to submit a paper, so you still have some time to do that. A call for oral presentations and panel discussions will be made in January of 2024. We encourage you to go out to the website to see updates as we progress through the process of getting registration open. So thank you for your time reviewing that website. Thank you to our presenters today and to Eric for moderating. For those of you watching us on YouTube, please like the video and subscribe to our YouTube channel. If you'd like to follow up with us, please feel free to reach out to admin@IBPSA-US. Thank you all and have a wonderful rest of your day.